So whole idea is, I talked to you already, hydrodynamic relations is nothing new because you learned fluid mechanics and all that. So you learned before. That doesn't mean that. That means you still remember. Maybe some of you may not remember that. So that's another reason I went through the conservation law. Conservation law means conservation of mass, momentum, and energy. Then driving down the relation for really pressure can be expressed as a function of the rho, mass density. That's what we did on Friday. Then using that, the basic relations, we are going to derive very important equations for the underwater shock equation, which is equivalent. Welcome back, Joel. Yeah, that's good. Basic underwater shock relations, or you can say underwater acoustics relation. Our interest is not the contact explosion. Our interest is what happened to the target in the water or floating on a free surface when explosion occurs a slight distance away from the hull. Okay, I mentioned to you last week. If you are worrying about the contact explosion, regardless of the situation, it will puncture the holes in the hull and internals. So in that basis, this underwater acoustics approximation can be, the result can be used for the underwater shock analysis. That point is very important. Okay, that's what U.S. Navy, Australian Navy, any Navy, the underwater explosion problem, when they deal with, that's the way to do it, okay? I'm not talking about the contact, I'm not talking about the detonation physics, which means what happened in the vicinity of the charge at the time of explosion. A little bit away means the shock wave detonation velocity. How much was the speed for detonation velocity? What's the speed? Detonation speed. What's the speed? In the water, of course. Okay, you are saying who cares? What's the detonation speed in the water at the time of explosion? Chong is ready.
I guess
Say 8,000 meters per second. Approximately, okay? About 8,000 meters per second. What's the acoustic velocity in the water? I'm keep asking the same question just to make sure that you remember at least those quantities, which is, Yongyan, how much? 1,500 meters per second. So as detonation speed really propagate at the time of explosion, it will propagate in radial direction. Then it will converge down from 8,000 meters per second down to 1,500 meters per second, very fast. It's not going to take more than a few milliseconds. 1 millisecond is thousands of 1 second. So in few milliseconds, it converges down to 1500 meter per second, then propagate in the underwater acoustic velocity. That's what we are using it, okay? So that's why I call sometimes underwater acoustics equation or underwater shock wave equation is the same in a sense. I'm not dealing with the detonation speed, rather the acoustic speed in the water. So we have done 3 conservation law, then pressure density relations is coming right from the conservation of energy. So this is what the final equation forms. E is what? Capital E. Which means you haven't even looked up the notes. I want you to at least look up the notes and prepare. Otherwise, the lecture is meaningless. Okay. E, capital E is internal energy. Okay, simply say internal energy. P is shock wave pressure, you can say. In an acoustic sense, it's acoustic pressure. And rho is mass density of the fluid. So that relation is all derived down from the basic motion down to the conservation of energy equation. But E here is internal energy of fluid per unit mass. So which means mass is equal to 1. That's what we used in the process of deriving the equation. So now from here, it's very clear the pressure is a function of the rho for the given the data for the internal energy, okay? So here, pressure density relation, I say internal energy E can be expressed as a function of pressure and the density as a thermodynamic variables. And this differential can be written by the chain rule, okay? It's nothing but the chain rule. 3 parameters, E, rho, and P, okay? So then bring back the conservation energy from here. Conservation energy, you can rewrite the different forms. I think I covered this Friday, I feel. Then substitute into E to D. Then you have, I think I did Friday. And you see the implicit relation, which you can say, I can say, which is solvable. You can compute. So you can compute that. So you can eventually solve P as a function of the rho, where initial value of the P and rho are known. EP and rho relation is known from a thermochemical data for the given conditions. So what I claim here is P can be expressed as a function of the rho. This is the rho, okay? And the square root of the dP over d rho is a very important parameter, which is called the acoustic velocity in the medium. Okay, so this is all conservation law here. And this chapter 2, I spend really, I don't know whether you notice or not, I spend some time to go through quite detail. I could just skip it But this particular chapter I spend quite a bit. And chapter 3 is not spending much time. And chapter 4, scaling, chapter 5, fluid structure interaction. Everybody's talking fluid structure interaction here in ocean systems engineering. But whenever you see the two media is interface or interact, then you have to deal with the effect of each other. So now with the knowledge of hydrodynamic relations, which we saw in 2.2, and we're going to look at the underwater acoustics wave, or you can say underwater shock wave. So basic assumptions, 3 or 4 basic assumptions are we're going to deal with. So with reasonable assumption. So for underwater acoustics or shock wave, sufficiently small disturbances in a liquid by the external source is motions, wave motion, as shock wave or acoustic wave propagate, fluid particle doesn't take much, the deformation. So in reality, as I might mention to you, I can stand maybe 50 meters away, about 25 meters away from the shore in the reservoir. Then we put 60-pound HBX1, which has about 50% stronger than TNT. And I see the situation when the explosion occurs and nothing, no motion except the color of the surface of the water is changing. As I recall, it darkened the color of the surface of the water because I think it's at the time of explosion, it compresses the water. So no motions. Is it just for 1 second period? No, instantly, no motion, but color changes, and it propagates radially. Then right after, then fluid particle just took off and plume occurs it, okay? So in reality, sufficiently small disturbances in a liquid with external source means at the time of explosion, everything is calm and good. Then second assumption, density changes insignificantly compared to its initial value. Initial value, rho naught. So as I mentioned, I use rho naught, subscript, I use when the value is near constant. In this case, what I'm claiming here is the mass density of the water, fluid or water. We are using mainly water. So water is a constant. In other words, d rho, del rho over del x, del rho over del y, del rho over del z is equal to 0. What does it mean for this equation set? Spatially, rho is constant, right? Rho is a constant, whether I pick up that position, this position. You can say for underwater shock analysis, you can assume the constant. However, when you deal with underwater acoustic propagation, talking about 100 kilometers away, then you can say it's a constant because its thermal layer is all there, and depth is also pressure changes as it go down deeper. So there is so-called caustic caustic effect, and I recommend you take underwater acoustics course. Professor Sung-Young Kim is going to deliver the lectures, I think this spring or the next fall. So he is oceanographic science man. I think would be most appropriate. I didn't take underwater acoustics course as a formal course, but I, of course, sat in when I was in Naval Postgraduate School. But I feel it would be better to lecture the underwater acoustics subject who not only major the underwater acoustics, but actually conduct the research and involve actual testings and so on, okay? So this is a spatially constant. That's fine because we are not dealing with a shock wave propagation for thousands of meters, okay? In the vicinity, it's more than vicinity of the target, which means it's surface ship and submarine. Maybe you're dealing with 500 meters, things like that. Then this assumption is very, very good and simplifies pretty difficult situation. However, spatially constant, okay? But that doesn't mean that del rho over del t is a constant. It's not. As I mentioned Friday, del rho over del t, if rho is independent to the t, then what you are claiming? You're talking about what? Incompressible fluid. If it's incompressible fluid, of course that's ideal fluid, but the wave doesn't propagate. But we want to have acoustic wave in motion propagate. So by looking at the rho versus time t, rho naught is like a mean value of the motion, mean value of the variation of the rho. It has a small time-dependent variation, but spatially you can assume it's a constant. You can make a constant. Strictly speaking, rho is equal to rho naught plus the del rho, the variation of the rho, time variation. But as approximation, that is equal to rho 0, okay? So this assumption is a second assumption. Particle velocity, you are dealing with the fluid particle velocity plus the underwater acoustic velocity, which are two different things. Underwater acoustic velocity is like 1,500 meters per second, but the fluid particle velocity you are dealing with is, for ship shock situation, actual experiment, you are dealing with about 12 feet per second, which means about maybe 3.5 meters per second. So it's a totally different ball game. Fluid particle velocity, okay? Why I'm emphasizing fluid particle velocity, for the rigid body, if you consider ship as a rigid body, you can, as approximation, as a crude approximation, you can assume the ship is a point in the water. Point means it's here, is really a fluid particle. You can assume the ship is a fluid particle, then you can consider the motion of the fluid particle as approximation to looking into the motion of the ship. Submarine, same thing, which is similar to when you're dealing with a satellite, or when you shoot up the wells, it's a satellite. I think Naraho, right? Naraho. They are ready to shoot up on 29. Yes or no? 29th, they're gonna try to lift 29th. No? Who cares? Anyway, when you put it up, the satellite on the orbit, two things you are dealing with. One is the motion. Think that satellite as a rigid body, and you are considering the motion of a rigid body and going around the orbit. Okay. Then second, now you have to going into the satellite is a shell, maybe membrane shell, or you have a boom, which is like a truss kind of the element, or beam type of the element. You have to conduct, then a motor is also there to make a motion to turn the satellite in the orbit, which is in the vacuum condition. There is no other excitation force in there. Then you have to study motion, internal, the satellite motion itself. For the ship motion, whether it's a surface ship or submarine, then you are dealing with the motion by the external shock. Then you study into conduct analysis. Basically, structure motion analysis, and you have to consider the interaction between the fluid and the shell. So that's why you always come up in ocean engineering, always FSI. But in this case, you could say acoustic structure interaction or acoustic solid interaction is what that is. When I give a lecture, I just talk in addition to the lecture note, what I can think of, which I already told you about it. And this is a surface ship hull, pretty rigid. When I did explain to you before, but once again, then you will not forget, but remember. The shock wave of 1,000 megapascal hit, okay? Hit the surface ship, hit the hull. 1,000 megapascal hit it. And it's not solid, it's not rigid in a sense that it has a plate as a hull. You know what's the thickness of a hull in the naval ship? Yongyun, you're a naval officer. What's the usual thickness? 10 millimeter. Let's say 10 millimeter. It's a pretty flexible 10 millimeter. Okay? And the thickness could vary, but 10 millimeter is a pretty good size. When shock wave hit it, okay, 1,000 megapascal, what would be the pressure experiencing by this hull plate? Anybody can tell? You are the designer. You are in the position to say something about this. What is it? Abdullah? what you have in mind. I'm in the position to design the hall. So one of the analysis person say 10 millimeter, then you have to really design the hall size, thickness, for example, to resist, okay, for such a shock pressure, which is 1,000 megapascal. So you have to get some idea the range of the pressure that the hull would experience. What would be it? 한철, what would be it? You follow my question? 무슨 말인지 알아? 응? 몰라? 왜 몰라? 이게, Abdullah, you follow me?
Yes.
Okay. So the analysis person brought the design drawing, and as I look at it, he picked up the hull thickness as 10 millimeter hull thickness. Then I have 1,000 megapascal, the shock wave is hitting. So I'm in the position whether this hull size, thickness size, is good enough to resist 1,000 megapascal shock pressure or not. To do that, I have to know what is 1,000 megapascal. I have to really know what would be the pressure, shock pressure, actually experiencing on the hull. Is it 1,000 megapascal, or is it lower, or is it higher? You have to have a judgment because you are taking the course. If you say, I don't know, which means Yongshin didn't do a good job. Hmm? What would be it? Idea, right? You are the master's degree person. You are the supervisor. Yongyun is a naval officer working as a supervisor of ship. In Navy, they have a supervisor of the ship in any shipyard, naval shipyard. So you're in the position, okay, I have to design this based on what shock pressure. 1,000, you can easily say, oh, this will experience, you said 1,000 megapascal, then this guy will experience 1,000 megapascal. That's what you said. Is it 1,000 megapascal? Hmm? If it's rigid, what would be the pressure this rigid surface would experience? Abdullah, louder. 1,000 megapascal. 경석. Who cares? I don't know. How about Yonggyun? You could say, I was away last week. I don't know. Chuil. I was away last week. I don't know. 정호. Higher, lower, down, or 1,000. See, that's correct. But I am insisting, as an engineer, get the feel of it always. Get the feel of it. That's very important. Not just by memorizing. You could use, of course, your memory. That will help you in your career. but 감을 잡으라고. As an engineer, I want you to have a feel as engineer. That's very important, okay? One time, I remember when I talk higher is a 2p or less than 2p. I talk about it. You remember? Maybe not. But today I want you to remember. If this is a rigid surface, then 1,000 megapascal come shock wave hit the target. And I didn't say anything about the damping, absorption of energy on the surface. You could imagine if it's a bare surface, it's simply the rigid, then when it hit it, this will experience 1,000, of course. But it's not stick to it. It will reflect back all the energy back, pressure, which means I have to this on the surface. When shock wave hit it, the shock wave has to kick the surface physically, kick the surface. Then it will reflect. So 1,000 megapascal, this will experience by so-called the incident shock wave, incoming shock wave, and it will reflect. If there is no energy loss, it will reflect back the 1,000. Then it has to kick the wall with 1,000 megapascal. If this is rigid, how much does it going to experience? Another 1,000 megapascal. So this guy, who is solid, rigid, then this guy's surface will experience 2,000 megapascal. Make sense? Say yes. Doesn't make sense? Raise your hand. Then you can go out. So 2,000. But if this is a flexible 10 millimeter, it's a flexible. When I punch it, it doesn't say, okay, I'm Mike Tyson, I'm strong. You punch me, I'll stick to it. That's rigid. You punch me, I'm not Mike Tyson, I'm Young Shin. I have a soft belly, so when I punch it, it can move, right? It's a flexible, right? It's so flexible. So as I receive the punch, flexible means I can move my belly back, so which means less damage, less pressure. So when I hit it, how much do I experience? 1,000 megapascal, because it's incoming, right? My belly experience due to the flexibility of the hull. Some will be what? Bounce back, right? Bounce back plus absorbing takes 1,000 megapascal. Some absorbed by the hull. Some will reflect. So actual P, right? Actual pressure I experience is incoming pressure 1,000 plus less than 1,000 megapascal. Whatever reflect, some absorbed. Okay, so whatever the reflected pressure, that's what kicking my belly. So it could be depend on flexibility. Okay, it could be like that. I mentioned to you Friday without giving you the derivation. We're going to do the derivation this week. P is equal to rho C. pressure, shock wave of pressure. V is the fluid particle velocity, I said. Or I can replace this guy as this is like a plate, this is air, this is fluid. When it comes right out there, I can say this will take off with some velocity. Whole plate will take, take off with a certain velocity. So rho C impedance, fluid impedance. V is, you can say, motion velocity of plate. Then that much of the pressure then the plate can absorb. All others will reflect back. It's in chapter 5. Chapter 5, okay? For fluid structure interaction. Very simple so-called Taylor plate theory, and which tells very clearly how the solid and structure interacted together. What does it mean, interactions? So all such things you can experience. Okay, so third, particle velocity is always small. It's not the 5,000 feet per second, 1,500 meters per second. Fluid particle velocity, as I mentioned, you are dealing with something like 10 to 15 feet per second, 3 or 4 meters per second. That's the usual motion, very small. And very small, then if you have a term which you saw this in the conservation of momentum, which you will see in a minute again, and this is a really small variation of a fluid particle with respect to the spatial point. X is a spatial point, very small. Small times small, smaller. Then you can approximate set equal to 0. For any underwater acoustic wave in conjunction with the explosion, underwater explosion analysis, okay? 3, assumption, very reasonable, good assumption. That's what I'm talking about it. Then you remember the conservation of momentum. Conservation of momentum is right here. This is equation of continuity or conservation of mass. This guy is conservation of momentum. This V vector is a fluid particle vector, fluid particle velocity vector, UVW. And this is conservation of energy. So over here, what is this? Conservation of momentum is sometimes called Euler equation, as a conservation of mass is called the continuity equation or equation of continuity. So this is called the momentum equation. Momentum equation, conservation of momentum, or Euler equation is all same, no differences whatsoever. And this equation, total derivative of fluid particle velocity with respect to time t, this you can expand this using the chain rule we did, and the v is a function of time t plus the position x, y, z. So if you take the chain rule, then you can come up this. The v times gradient, spatial operator gradient, v times over here, u times right here, So this is nearly equal to 0 for underwater acoustic wave problem. So this can be reduced down to rho del V over del T is a del partial, not the total, is equal to minus gradient P. Gradient P is like this, right? Then using the assumptions here, I can reduce down this equation as the first term is equal to minus gradient P. Rho you can deal as the constant because it's spatially constant. Then I can really reduce down the conservation of momentum equation as this equation. This is a very good equation to be used for underwater acoustic analysis. Del V over del T is equal to minus 1 over rho naught gradient P. It has a name on it. It's not exactly the same as the conservation of momentum. It's not Euler equation. It's really reduced momentum equation, okay? So remember, if you keep looking, you will remember. So it's reduced the momentum equations, okay? Remember this, reduce the momentum equation. So that's used for underwater acoustics. Then now this page is really some variation is what I'm doing to make it clear. I think in your note you see my arrow, right? I think you see my arrow. The Wednesday, I'm going to give you the complete lecture note handout. Higyu really spent some time. He's my chogyo, you know, as he's doing doctoral degree. So he put it all together. My notes will give you the Wednesday morning. Then you don't have to print from the file we are always attaching. So here, this will ease up how it fits. What's this equation you call? Songtae. What's called this equation? That's what a lot of time I hate to use PowerPoint because, but this will accelerate the speed. So that's why I'm using 3 topics in one course. I don't think I would do again. But this is good for you. Anyway, this is a conservation of mass, right? So from here, I said or means I remove this rho outside saying rho naught. Why? Because divergence is gradient dot, right? Gradient is spatial operator. Then spatially, rho is constant. That's what the basic assumption we give. So rho naught is outside. P is a function of the rho. That's what we talk, right? After we look at the conservation of energy, we concluded P is the function of the rho. So del P over del T, you can express as a dP over d rho is only one parameter. S naught is adiabatic state, no heats in and out. And d rho, del rho over del T is equal to this. This is called the C naught square. So I wrote here C naught is equal to square root of dP over d rho. C naught is really acoustic speed in the water, okay? So this can be expressed as this guy. So del P over del T is equal to C naught squared. C naught means it's a constant. C naught is really near constant. But if you say C naught, acoustic speed in the water in the Indian Ocean and the Pacific Ocean, of course, which is different. So I provide the equation for that, which is also function of salinity and temperatures. So this is here, then 1500 coming in. So from this equation set, del rho over del T, I take this C naught square, move to the other side here, is 1 over C naught square del P over del T, which is equal to, we bring it from the conservation of mass or continuity equation, bring it down here, del rho over del T is minus rho naught divergence V. This is what right here is. So here is minus coming here. So you have this is equal to this is equal to this, okay? It's nice to, easy to look, but it's nice to derive yourself. Then I'm dealing here, remember, dealing with the wave motions, okay, not the fluid motion. Why? Because we apply the assumptions to change from hydrodynamic wave motion to the underwater acoustics motions, okay, wave motion. So now we're going to differentiate, just to look at this second term and third term. So differentiate with respect to T once again. Then from here, differentiate once again. I put the rho naught same to make the same as here. Then this term, del V over del T is equal to minus 1 over rho naught del P, which is shown, I think it's in the next page. And this guy is del P minus del P, which is minus minus cancels up, then has a Laplacian del square P. So this is what the reduced momentum equation one page before in this second half, which is nothing but the momentum equation, but it's a reduced momentum equation. Take a look at the previous page. So this is what the equation said is. Then if you, the same thing, then you have beautiful, this equation. Have you seen this equation before? Don't say no. This is a wave equation, not the hydrodynamic equation. This is a wave equation. P is like acoustic pressure, or for shock analysis problem, this is what the shock pressure is. And C naught is acoustic speed in the water. Okay? Got it? So this is a wave equation. What we did first was to look at the underwater shock problem. We get the equation set we need, which happen to be here, is nothing but the acoustics equations. Now you are in the position to solve this wave equation for plane wave. And another wave is spherical wave. Spherical wave is when explosion occurs, when your target means it's really a ship or submarine, is close to the charge, then at the time of explosion, the shock wave is spherical. It has a curvature in it. But when the charge is far away, which is called the far field explosion, far away, this curvature is getting almost flat, right? Which is called plane wave. Plane wave you can call as a one-dimensional wave. No curvature effect. But however, the pressure, shock pressure, is affected by the curvature because the shock pressure is inversely proportional to the R, the radius of the wave, radius of spherical wave, 1 over R. If radius is very far away, 1 over R become converge to is what? 1 over R. R is large. What happened? 0. So curvature effect is not there for long propagating wave. Okay, nuclear explosion. Curvature effect is none. If it's too close, all you have to do is a goodbye. It has to, if it's so far, then makes sense for the survivability, but nuclear explosion is totally a different animal. But near-field explosion, Cheonan naval ship, near-field explosion, 6 meters away from the ship. Of course, the curvature effect is tremendous. That's what happened. So wave equation. So I'm going to, Wednesday I'm going to talk specialize or get the result, answer, solution for plane wave, which is one-dimensional wave. Assume moving in the x direction. You can assume move in y direction or z direction. So we're gonna look at the detail for plane wave and the spherical wave. Then we'll move on. Pengxing, don't get back the shingle. It's all done, right? So Pengxing came back. I'm glad he's really live and well. Okay, I'll stop here and I'll see you Wednesday.